Welcome to Unit 2, Lesson 4, Proof by Mathematical Induction. This is the first of 3 videos for this lesson, and by the end of the 3 videos, you should be able to use proof by induction to prove statements involving a positive integer n, the sum of the powers of integers, and finite differences of sequences. So let's first in this video discuss proof by mathematical induction. Okay, to begin, let's introduce and consider the following pattern. Notice 1 is the first term of this sequence, and I can consider it as 1 squared. Look at what happens when I take the first 2 terms of the sequence, 2 squared. The first 3 terms of the sequence, I get 3 squared. The first 4 terms of the sequence, I get 4 squared. So if we want to generalize this pattern, we are taking the sum of the odd integers. So if I wanted to add the first 7 odd integers, it would be 7 squared. If I wanted to add up the first 20 odd integers, it would be 20 squared. So we could find a formula that would generalize this pattern. We could say that you would take the n number of odd terms and square it, or the sum from n equals 1 to infinity of 2n minus 1 would equal n squared. Okay, but here's kind of the problem. This is what we've been doing in the past. We've used inductive reasoning to deduce a general rule based on specific facts. So if I go to this slide, what we just looked at was a pattern, and these were specifics. Well, there's a quote from your book that I thought was worth rewriting. Although this particular formula is valid, it is important for you to see that recognizing a pattern and then simply jumping to the conclusion that the pattern must be true for all values of n is not a logically valid method of proof. So really, you derived a formula based on pattern. You did not prove a formula based on pattern. So this is where mathematical induction comes in. For example, we had a famous mathematician, Fermat. He's known for Fermat's last theorem. He's a French mathematician, and he jumped to the conclusion when he tried to prove that all of the numbers of the following form, 2 raised to the 2 raised to the n plus 1 for n equals 0, 1, and 2, and so on, were prime. So let's take a look at what he was talking about. He inputted 0 and outputted 3, and I've got the slide from the graphing calculator so you could kind of see the work. When he inputted 1, we got 5. When we input 2, we get 17. 3, 5, and 17 are probably very easy for numbers for you to recognize that they're prime. Now, when we put in 3, we got 257. It might not be obvious, but it is prime. He put in 4. 65,537, his 4th term of his sequence, is indeed prime. But then our friend Euler, he came in, spoiled the party. Our pal Euler found that 641 times 6,700,417 yielded 4,294,967,297, which was the 5th term of Fermat's sequence. So Fermat's conjecture flushed down the proverbial toilet. If he just looked at the first 4 terms, you would think that his general formula was true for all cases, but in fact it was not. So this is where mathematical induction comes in. Just because a pattern seems to work for several values of n, you cannot simply decide that it is valid for all values of n without going through a legitimate proof. And mathematical induction is one legitimate method of proof. You'll be able to add this to your repertoire of 2-column proof, flowchart proof, or paragraph proof. So what is the format of proof by induction? Not to be confused with Fermat of proof by induction. Stupid math joke. Okay, moving on. There's 3 parts. The first part of mathematical induction requires us to prove that the base case is true. The second part requires us to assume. Yes, I'm writing assume. And I get it that you've always been taught that when you assume things, that's what it does. But we will assume that when we input a value of k into the formula, we're going to assume that that's true. Our third and final step, and this is where you will see a little bit more work done, is we will prove that k plus 1 is true for every positive k. So to repeat, the first step of mathematical induction, you have to prove the base case is true. Then we assume that inputting k into the formula is also true. we will use that information to prove that k plus 1 is true for every positive k. What's interesting is that we will prove that p sub n is true for all positive integers n using this method. And we will revisit this after we do a concrete example. For example 1, we are going to prove using mathematical induction that the partial sum on the left, I equals 1 to n of I, is equivalent to the formula on the right, n times n plus 1 over 2. Before I show you how to prove that the sum is equal to that formula, let's just remind ourselves what that sigma notation means. What it means, the first term, I, is 1. The second term when I input 2 is 2. The third term is 3. The fourth term is 4. And we're going to keep adding those terms all the way until I get to the upper bound of n. And what we're saying is we want to prove that that is equal to n times n plus 1 over 2. Just some specific examples to show you that this works. But again, these are specific examples. That doesn't mean that this is a proof. But just so you understand, let me look at the partial sum from I equals 1 to 4. This means I would add 1 plus 2 plus 3 plus 4, which yields 10. If I use the formula n times n plus 1 over 2, when I input 4, I get 4 times 4 plus 1, which is 4 times 5, which is 20 over 2, and it also yields 10. So I just want to specifically show you that we had a case where the summation on the left equals the formula on the right. I picked 7 to showcase the same thing. If I want to do the partial sum from I equals 1 to 7, I would add the first 7 integers, which yields 28. But if I use the formula 7 times 7 plus 1, which is 7 times 8, which yields 56, and divide that by 2, it also yields 28. So again, these are specific examples of why the summation I equals 1 to n of I, it equals n times n plus 1 over 2. But now we want to prove that. We want to make sure that, like for Mott, we don't want to have somebody come up and flush our specific formulas down the toilet. We need to prove, using mathematical induction, that the general formula of the infinite sum works in all cases. So here we go. Our first step in proving that the partial sum is equal to n times n plus 1 over 2, we have to prove the base case is true. So to prove the base case is true, we prove this for the first term. So my first term in this case is 1. The sum from I equals 1 to 1 of I is simply 1. Now, if I input 1 into the formula, 1 times 1 plus 1 is 2. 1 times 2 is 2. And when I divide that by 2, I get 1. So I have just proven that equals the sum from I equals 1 to 1 of 1 equals the formula 1 times 1 plus 1 over 2. We've just proven the base case to be true. Now we're on to step 2. On step 2, you have to make an assumption. You have to assume that P sub k is true. What does that entail? You substitute k into the equation you're trying to prove. So if I take the summation from I equals 1 to k of I, this means I would be adding 1 plus 2 plus 3 plus 4 all the way up until the kth term, since it's my upper bound. We are assuming that it is true that k times k plus 1 over 2 is true. Third step, I'm going to do the same thing, but we're going to prove that if I input k plus 1 into the statement I am trying to prove, that it is true. So here we go. Okay. If I think about this, I would take the summation from I equals 1 to k plus 1 of I, and this means I would add 1 plus 2 plus 3 plus 4 all the way up until k, and then I would have to add the upper bound of k plus 1, and we are trying to prove that it is equivalent to k plus 1 times k plus 1 plus 1 over 2. Now, if you look at the 1 plus 2 plus 3 plus 4 plus all the way up to k part, we made the assumption in step 2 that it was equivalent to k times k plus 1 over 2. So I'm going to substitute k times k plus 1 over 2 for that part of my sum, Then I have to add the k plus 1. And then after adding 1 plus 1, we would simplify that we're going to prove that that equals k plus 1 times k plus 2 all over 2. Now I can get a common denominator. K plus 1 can have a common denominator of 2 because 2 over 2 is 1, and if I multiply any expression by 1, it stays its value. In the next step, I put the left-hand side as one fraction. And notice how each term has k plus 1 in common. So when I factor out a k plus 1, I'm left with k plus 1 times k plus 2 over 2. And you have just proven that the left side is equivalent for the right side, and you had to substitute in a value that was assumed. So here is the part that's weird and you're going to have to simmer over. In mathematical induction, by proving the base case is true, we made an assumption that it was true for k, but then we proved that k plus 1 is true. We can now say that it's true that I equals 1 to n of I is true in all cases for n, and that it would equal n times n plus 1 over 2. So if we revisit that earlier sentence that I had before, because we showed the base case was true when we inputted the 1, and we have proven that k plus 1 is true, we can say this formula is true for all p sub n. Another way to think about this is since p sub 1 is true, then the next term p sub 2 is true because it's just the next term p sub k plus 1. So if 1 is true, 1 plus 1 is the second term. The second term has to be true. If the second term is true, then the third term has to be true. And if the third term is true, then the fourth term has to be true, and so on, because it's always one more term than the previous, and so on. So another way that you can kind of think about this, it's like knocking down dominoes. If they are set up correctly, all you have to do is knock down the first domino. The first one knocks down the second knocks down the third, and so on. So think about that. This person just pushed down 1. All he pushed down the base case, assumed that the next domino would indeed knock down the domino after that, and by proving that it worked for the next domino to be pushed down, then we notice that all of the dominoes, the domino effect, it's always happening until infinity. Okay, yeah, this is just fun. So if you don't really like the domino part of this video, then just fast forward. I'm mesmerized. Okay, enough of that, but I just knew that there might be some of you in there that probably still wanted to watch it, so I kept it going. All right, so that's the whole premise of proof by induction. You prove the base case, you assume that it's going to be true for an input k, and if you can understand that it works for k plus 1, then it has to work for all of them. So in that video, we proved the base case, the first domino, and we assumed any domino in the sequence is knocked down, and then we proved that the next domino would be knocked down behind it. For example 2, we're going to prove another formula is true for every positive integer n. So I give you on the left the series 2 times 1 plus 3 squared plus 3 to the third plus 3 to the fourth plus 3 to the fifth, all the way to the 3 raised to the n minus 1 power. And we are going to prove that is equal to the general formula 3 to the n minus 1. by mathematical induction. So our first step of mathematical induction is we have to push down the first domino. We've got to prove that the base case is true. So the first term of the series is 1. So if I take 2 times 1, which is the first element or the first term of the series, that would equal 3 to the first power, and I'm using n equals 1 because it's my base case, minus 1. When I do the simple arithmetic, 2 is equal to 3 minus 1, and 2 is equal to 2. So I have successfully proved that the base case is true. I've knocked down the first domino. The second step of mathematical induction is that we have to show that if we pick any k, any term in the series, that we're going to assume that it's true. So I'm going to assume p sub k is true. If I take 2 times 1 plus 3 squared plus 3 to the third plus 3 to the fourth plus 3 to the fifth, all the way to the 3 raised to the k minus 1, because I'm substituting in k for n, it should yield 3 to the k minus 1. We are assuming this is true. Now for the next part. The last part of mathematical induction is to prove that k plus 1 is true. So we're going to assume that every domino is going to push down the next domino. So if I want to prove that k plus 1 is true, my series would look like 2 times 1 plus 3 squared plus 3 to the third plus 3 to the fourth plus 3 to the fifth. Then 3 to the k minus 1 power is the preceding term. And then I'm substituting in k plus 1, and let me kind of scroll down here so that you can see the original. I'm substituting in k plus 1 in for that n, minus 1, and that should yield 3 raised to the k plus 1 minus 1. Now, that 2 would have to be distributed to every term in the parentheses. 2 times 1, 2 times 3, 2 times 3 squared, 2 times 3 to the third. I'm going to choose to kind of group them the following way. I have to take 2 times 1 plus 3 squared plus 3 to the third plus 3 to the fourth plus 3 to the fifth, all to the 3 raised to the k minus 1. And then I'm going to distribute 2 to the final term of 3 raised to the k plus 1 minus 1. Why did I do that? Because the first part of that, the 2 times 1 plus 3 squared plus 3 to the third, all the way to 3 raised to the k minus 1, is essentially the assumption from part 2. I can substitute in 3k minus 1 for that portion of my series. K plus 1 minus 1 simplifies to just the power of k, and then I bring the right-hand side down. In the next step, I drop the parentheses, and I rewrote 2 times 3 to the k with a dot instead of parentheses. Next step, all I did was reorder my terms using the commutative property of addition. Why did I do that? Please look at the parallel problem that I have here on the left. A reminder about how exponents work. When I have the same base raised to the same power and I add them, I can simply add the coefficients together. So that's what I have here. I have 1 times 3 to the k plus 2 times 3 to the k. So that means I have 3 times 3 to the k. 3 is raised to the first power, understood. So when I use my laws of exponents, this yields 3 to the k plus 1 minus 1, and that indeed equals 3 raised to the k plus 1 minus 1. We just proved that if we input k plus 1, that it is true. So by mathematical induction, we can conclude that the original formula holds for all positive integer values of n. A collection of useful summation formulas. These are printed in your textbook. I just felt that I should mention them. It is problems 13 through 16 in the homework set for you to prove them. We already did problem 1. When we have I to the first power and we're just going to add all of the integers, we can use the formula n times n plus 1 over 2. In the second summation formula, now we're taking all the integers squared. And when you take their sum, you yield n times n plus 1 times 2n plus 1 over 6. In the third one, we're taking all of the integers to the third power, which yields n squared times n plus 1 squared over 4. And then, as you can read in the fourth and the fifth summations, we're taking all of the integers to the fourth power and all the integers to the fifth power, and it yields those following formulas that we will be left to you to prove in the homework set. So, for more examples, please refer to the text starting on page 586, specifically examples 1, 2, and 3, because these are like identities. You really just need to read several examples because all of them are a little bit different. And your learning opportunity number 1 that you can work on in class, next class period, is page 592, numbers 1 to 21 odd.